a long talk.
Thank you. I'd like to thank the organizers for the opportunity to be part of this wonderful conference. So, I'll be reporting about several works. Some of them are a little, let's say, older, maybe a couple of years ago. Some are more recent, and some are actually work in progress. And my co-authors are Jaime Burgos from Saltillo, Mexico, Maciej Kapiński from Krakow, Rafael de la Llaga from Georgia Tech, and Pérez Serra from Barcelona. So, just a very quick overview of the Arnold Diffusion problem. So this is a famous problem dating from a question posed by Arnold in 1964. So first, let me recall the question in a slightly informal way. So the question is whether if you start with a typical integrable Hamiltonian systems of more than 2 degrees of freedom, and if you apply to this integrable Hamiltonian small perturbation of a generic type, whether you can show the existence of trajectories that travel a large distance, that is a distance of order 1 in action with respect to the perturbation epsilon. And let me quickly phrase it in a different way. So one can start with autonomous Hamiltonian systems, which of course the energy is preserved along trajectories, and apply a time-dependent perturbation which can be periodic, can be quasi-periodic, or can be even more general. Some recurrence of the dynamics will be sufficient, and prove that there exist trajectories for which the energy, which is no longer preserved for the non-autonomous case, for which the energy changes by a quantity of order 1, which is independent of the size of the perturbation. And if you do very simple numerical simulation, if you start just with distribution of initial conditions and you let them diffuse, you'll see that some trajectories go in some direction, some trajectories go in another direction, and basically what you have to look for, what are the initial conditions for which you can achieve, let's just say, a constant increase in the action throughout over time. So there are a bunch of terms here that are quote-unquote, like typical, generic. So I'll try to be a little bit more precise on the following slides. So the problem has been traditionally categorized, classified in the a priori unstable case. So this is the case when in the unperturbed system there is hyperbolicity, there are hyperbolic variables. And the classical example is you have a rotator, or a generalized type of rotator, a system of penduli, and some perturbation. And for this problem, one can prove the existence of diffusion for which typical, so remember that typical refers to the unperturbed Hamiltonian. So typical is anything, so there are no conditions here that we require in order to obtain diffusing orbits. And generic, so genericity here has been achieved in the open and dense in some class of CR functions. So we are only going to talk about CR systems, so we are not going to talk anything about analytic setup. So for the a priori stable case, there is no hyperbolicity in the unperturbed system to begin with. So the hyperbolicity is created by the perturbation itself. And the results that have been obtained in this setting are require a typical unperturbed Hamiltonian, and typical means convex and superlinear, and generic it's a weaker than open and dense condition, so it's the so-called Mather-Cast residual condition, which gives you a smaller family of perturbations. So this is like that was a very brief overview of the Arnold diffusion problem in the a priori unstable and a priori stable case. And there are lots of works in the a priori unstable case, and this is really a random selection of some references. So I just want to emphasize that there are several approaches, and some of them are geometric, some of them are variational, some of them combine geometric and variational methods. There are also semi-numerical approaches, and there are approaches that combine semi-numerical with geometric and so on and so on. So there have been many works on the a priori unstable case, and in the a priori stable case, progress has been more recently reported. So I would like to advocate in some sense for the geometric method. So let me stress what are the geometric objects that one can obtain in the models described above. So one can find the normally hyperbolic invariant manifold, or a chain of normally hyperbolic invariant manifolds. So that would be the a priori unstable case, and that would be the a priori stable case. So what is a normally hyperbolic invariant manifold? So let me just recall it briefly. So you have a manifold that is invariant, and in the normal direction you have stable and unstable directions, and the expansion and contraction in these directions dominates the whatever expansion and contraction you might have along the manifold itself. So one approach is to look at the inner dynamics, the dynamics restricted to the normally hyperbolic invariant manifold itself, and the outer dynamics, so this is the dynamics along homoclinics and heteroclinic orbits, so you have stable and unstable manifolds. We show that they intersect and we follow these homoclinic trajectories. So the inner and the outer dynamics, they do not provide automatically orbits because the inner dynamics lie on an invariant manifold, and the outer dynamics is just asymptotic to the invariant manifold. So you can obtain pseudo-orbits by alternating the inner and the outer dynamics, but you have to do an extra work to show that once you find some convenient pseudo-orbits, there exist two orbits that follow them. So some of the advantages of the geometric method is that at least in the a priori unstable case, you find explicit conditions for the unperturbed Hamiltonian, and you find explicit conditions for the perturbations. And these explicit conditions can be verified in concrete examples, such as from celestial mechanics. And then the diffusing orbits that you can find are orbits that you can construct explicitly. And one advantage is that besides analytical arguments for the existence of diffusing orbits, you can combine these with numerical approaches because it gives you a recipe of how to find such orbits. So what I show here in this cartoon is typically a picture for the a priori stable case, where we have not only a cylinder but a bunch of cylinders that have unstable manifolds in red, stable manifolds in blue. So you can go from one cylinder to itself, or you can go from one cylinder to another and follow the chain and so on. So now let me illustrate the geometric method on two examples from celestial mechanics. So one is a planar elliptic restricted three-body problem. And so the idea is that you start with a planar circular restricted three-body problem. So this is a given, described by an autonomous Hamiltonian. So the energy is preserved. So there are libration points. So let me focus on one of the points, the L1 point, which is of center saddle type. So for each energy level, there is a Lyapunov orbit that has stable and unstable manifolds that intersect transversally. But if you start at some energy level, if you start at some Lyapunov orbit and you follow the homoclinic excursion, you end up on the same Lyapunov orbit, you end up on the same energy. So there is impossible to gain energy in this in the planar circular restricted value problem. You add, instead of considering the motion of the primary circular, you take into account elliptic orbits for the primaries. So the eccentricity can be viewed as a small parameter. In this case, the Hamiltonian can be written as the one for the planar circular restricted three-body problem plus a small perturbation. And in this case, at least it's possible, it seems possible that you can have trajectories for which the energy grows. And this is a result with Maciej Czapinski and Rafael Ayave. So the result is the following. So starting with some small value of the size of the perturbation, epsilon 0, there is also some distance in the action variable, and whenever we have epsilon, a perturbation size bigger than epsilon but less than epsilon 0, you find the trajectory for which the action, or if you wish, for which the energy changes by at least the quantity rho. And of course, the smaller you take the size of the perturbation, epsilon, the more time you need to achieve that particular growth of energy. So, and we worked with some realistic parameters, so at least some of them are realistic. So we really looked at the Sun-Jupiter system, and we consider an energy level corresponding to the comet of Lemmas. So let me emphasize that we obtain a proof which combines analytical arguments with some numerical verification, but the proof is for all epsilon sufficiently small. So one thing that we do not do to achieve such a proof is like choose an epsilon small, prove there are diffusing orbits for that epsilon, choose another epsilon even smaller, find that there are trajectories that diffuse for that small epsilon, and so on. So you have an argument that works for all epsilon from 0 to some upper bound, no matter how small is that epsilon. Okay. And I'll explain the proof towards the end of the talk. And it turns out that, let me give you just one idea. It turns out that it relies heavily on manifold theory, and it boils down to the computation of one integral. So one integral will tell you if you can achieve such diffusing orbits. So the second problem is very similar. So we have three bodies in a in an equilateral triangle central configuration. So this is, and we consider a fourth body that has an infinitesimal mass. So this is a restricted four-body problem. And again, it turns out that if you focus near the lightest body in this configuration, and if you do a Hill approximation, you find 4 equilibrium points. 2 of them are of center-center type, 2 of them are of center-saddle type. So it's a very similar situation to the previous case. You change this to an elliptic problem, so you assume that the primaries move on elliptical orbits. Again, what you can do is consider the eccentricity as a small parameter, and you can start at a Lyapunov orbit and show that you find trajectories that go from nearby that Lyapunov orbit to another Lyapunov orbit, which is order 1 far apart. So it's just the setup is different, but the mechanism is the same. So, so this is a result with Jaime Burgos, and this is we are hoping to finalize the paper soon. So the motivation for this problem is we are interested in the Jupiter's Trojans, and in particular we're focusing on the Trojan called Hektor. So this is roughly located at L4, and it has a moonlet, and it's one of the few Jupiter Trojans with a moonlet. And there so Marchis and co-authors have a series of papers that started from astronomical observation of this moonlet, and these observations are quite poor, and they hypothesize that the motion of the moonlet is stable, but it's very close to instability. So what we are trying to study, and the work with Jaime Burgos is just a preliminary work in a very simple model, whether the effect of the eccentricity of the orbit of Jupiter can lead to diffusion, can lead, for example, to the moon to escape, either in the future, or maybe it's more interesting to look at the past, because apparently this moonlet was formed as a piece of the asteroid that was ejected. So maybe we can track backwards possible scenarios for the orbit of this moon. So as I said, so the work with Jaime Burgos is a very assumes a very basic model, but we have also work in progress with Jaime Burgos, Alessandra Ceretti, Catalin Gales, and my student Waiting Graham. And there is another bifurcation of this work with Rodney Anderson from JPL and my student, who are looking at other asteroids, not Hektor. And they are interested in actually navigation of a spacecraft around such an asteroid. So I think I can go faster on this because I already explained it. So the geometry for the planar circular restricted three-body problem for the four-body problem are quite similar. So you find for each energy level a Lyapunov orbit, and the stable and unstable manifolds intersect transversally. And in the planar circular restricted three-body problem, so once you do the Hill reduction, you can find analytically four equilibrium points, and you can see two of them there and the other two in the other picture. So in gray, what you see are the Hill regions, and so again, what we are studying here in the restricted four-body problem is that one object, the heavier is the Sun, the other one is Jupiter, the third one is Hektor, and we are studying the motion of the moonlet around Hektor. And because the moonlet is very close to Hektor, so doing this Hill reduction is quite helpful. The major advantage of doing the Hill reduction versus the restricted four-body problem is that you can compute certain things analytically. So this is like a standard type of work that you do. So once you do the Hill reduction, you can do Levi-Civita regularization, and you see the Hamiltonian becomes a polynomial, so you can see pictures that are very familiar to the lunar Hill body problem. So these are pictures that, there are some pictures that have been obtained by Carle Simon and Stuckey. So these are very similar ones, and they are almost identical for small mass parameter. If the mass parameter is large, the pictures, the dynamics is somewhat different. So, as I said, so we focus here on the two equilibrium points that are center and stable. So again, for each, so they are on the same energy level. For each energy level, there is a Lyapunov orbit around each of them. They have stable and unstable manifolds. They are homoclinic trajectories, and they are also heteroclinic trajectories. So this is a zoom onto the Hill region. And what is interesting, so these are the stable and unstable manifolds in the interior region of the Hill region. And these are the stable and unstable manifolds that go outside of the Hill region. So unlike the lunar problem, they intersect. So in the lunar problem, these branches of the invariant manifold escape infinity. But here in this situation, and it makes sense that because you are near L4, they intersect transversally. So you can have different ways in which you can diffuse. So you can diffuse in the inner region, you can diffuse in the outer region, or you can have going inside and outside and diffusing this way. So these are some pictures that show you the complexity of the intersections of the stable and unstable manifolds. I'm just showing that because I think they are beautiful, but they are quite familiar to this audience. So again, once you have a good understanding of the geometry of the unperturbed problem, going to the Hill perturbed problem, so now the small parameter is the eccentricity of the elliptic orbits, you can write again the Hamiltonian of the problem as the Hamiltonian of the circular restrictive four-body problem plus a small time-dependent perturbation. So the idea of the proof in both cases is exactly the same. So you have a normally hyperbolic invariant manifold in the unperturbed case, which is a cylinder. You use a standard theory of normal hyperbolicity to say that for perturbation small enough that cylinder survives as a normal hyperbolic invariant manifold. You study separately the inner dynamics and the outer dynamics. For the outer dynamics, you use this tool known as the scattering map, which was presented by Teresa in the morning. So I'm going to review it quickly. And the very important, very crucial part of this is that the scattering map is computable, and is computable by doing in terms of a convergent integral of the perturbation along a homoclinic of the unperturbed system. So in other words, you do not need to study the geometry of the perturbed system at all. So all you need to do is find the geometry, understand the geometry of the unperturbed system, and compute one integral, which is that you integrate the perturbation along one homoclinic, or maybe around two homoclinics of the unperturbed system. So this is quickly a review of the scattering map. So you have a normally hyperbolic invariant manifold, which is a cylinder, and you choose a homoclinic intersection. And for each point in the homoclinic intersection, you look at the stable fiber, you look at the unstable fiber, and the scattering map is defined by the foot point of the unstable fiber is mapped into the foot point of the stable fiber. And if you are doing a suitable restriction of the homoclinic manifold, this is diffeomorphism from an open subset of the cylinder to some other open subset of the cylinder. So in the unperturbed case, the scattering map, you can define it as a limit, and it turns out to be just a shift in the angle. And then you choose a pair of homoclinic orbits in the unperturbed system. You know you have an explicit formula of the perturbation, and you can compute the integral of the perturbation around the homoclinic, and this gives you the first order expansion of the scattering map. So you expand the scattering map in terms of the perturbation epsilon, and the first order term is given by this Mernikov type of integration. So here I'm just showing briefly that you are interested, in fact, in the derivative of this generating function with respect to the angle variable, and if you do some integration by parts, you can put this in an expression that it's easier to compute. So I'm not going to try to explain all of these terms. So all I'm going to point out is that these terms over here, the phi I minus, they represent the angle coordinate of one homoclinic. So once you've found one homoclinic, you can use it to compute the scattering map and the derivative. So basically, what you want to show, one possibility is that for each angle, so there are always several scattering maps available for you. So what you want to show in order to prove diffusion is that for each angle coordinate in the cylinder, there is always a scattering map that keeps increasing the action or the energy. So if you look at this expression of the scattering map, so you may need to apply the scattering map repeatedly in order to gain order 1 in the action or in the energy. So therefore, you need to be able to find a strip on which the scattering map keeps increasing the energy by an increment of order epsilon at a time. And you should be able to either to return to that particular strip or to show that there are two strips in which you can move back and forth and always keep increasing the energy no matter which strip you find. So this mechanism will give you only pseudo-orbits. So this tells you that if you apply the scattering map repeatedly, or if you have two scattering maps, if you apply the whatever scattering map is convenient for you to increase the energy, what you obtain pseudo-orbits of just the scattering map. So this is not true dynamics, and you have to do some extra work to show that there are true trajectories that follows these pseudo-orbits created by scattering maps. So there are two important results. So there are two shadowing lemmas. So maybe I'm going to start with the second one. So if you have a pseudo-orbit generated by applying repeatedly a scattering map, so this is the way the lemma is written, and if you have some recurrence condition that in our case are automatically satisfied, so then you can find true orbits that follows these pseudo-orbits generated by the scattering. So let me just try to explain it one more time. So you have one scattering map, but you can also have several scattering maps, and you apply it repeatedly, and this gives you some pseudo-orbit, and then this lemma is showing that once you find this pseudo-orbit that, for example, increases the action by order 1, there is a true orbit that moves very closely to this pseudo-orbit. So in order to prove this lemma, we need another shadowing lemma, which is even more general. So it says that if you have a normally hyperbolic invariant manifold, and you have one scattering map, and you also, which is encoding the information on the outer dynamics, but you also have the inner dynamics. And if you generate pseudo-orbits that consist of applying the inner dynamics for a large number of times, applying the scattering map, and applying again the inner dynamics for a sufficiently large number of times, then for these type of pseudo-orbits, you can get true orbits that move very close to these pseudo-orbits. So what I want to emphasize is that you have certain restrictions on how many iterates do you have to apply the inner dynamics. So the obvious I mean, there is an obvious condition that you have to apply for sufficiently many times, but there is a less obvious condition that whenever you apply the inner dynamics, you have to take into account the past history of the pseudo-orbit and increase the number of iterates depending on the past history of that pseudo-orbit. So, for example, you cannot use uniformly large number of iterations to generate these pseudo-orbits. You may need to, as you make progress, you may need to keep increasing the number of iterates of the inner dynamics to generate pseudo-orbits that can be shadowed in the way described. So what is the connection between these two results? So the connection is the following. So here you have the scattering map that you apply repeatedly, but between any two successive applications of the scattering map, you can use Poincaré recurrence to interject a piece of the inner dynamics. And that piece of the inner dynamics can be an orbit of arbitrarily long length. So you do that and you generate immediately, just by Poincaré recurrence, an orbit as a pseudo-orbit as above. And then, at the end of the day, you get a true orbit that shadows the sequence of pseudo. So one objection is, here I mentioned the Poincaré recurrence theorem, and at the beginning of the talk, I was mentioning that this approach is constructive and you can actually implement it in concrete examples, but Poincaré recurrence is an existential type of result. So these are very general type of lemmas that require basically no assumption on the inner dynamics. So in order to obtain this type of shadowing lemmas, you do not need to assume anything at all in the inner dynamics besides Poincaré recurrence that comes for free, because all the objects that are involved in this construction are symplectic. So, but what happens in real life situation, as in the examples that we had before, you have some information. So you have lots of orbits that are recurrent. So you have, in a nearly integrable situation, you can closely follow, for example, invariant tori. So you have several ways in which you can improve this technique of, instead of calling the Poincaré recurrence theorem, we can appeal to orbits that truly exist in the inner dynamics. So let me just go back and say something about how these pieces fit together. So there is this analytical argument. So the analytical argument tells you that all you need to do is a Markov type of condition, and this Markov type of condition, which boils down to a certain integral being positive or on some streak, or compute the integrals corresponding to two homoclinic intersections. Each of them is positive on a corresponding strip, and the two corresponding strips cover the whole angle domain, as you see here. So these curves represent that you have a homoclinic here where the scattering map increases the action, and here you have another homoclinic for which the scattering map increases the action. So if you are in this region and in that region, you can always choose your convenient homoclinic and the corresponding scattering map that keeps increasing the action. So that allows you to prove the existence of diffusing trajectories without necessarily exploring each epsilon sufficiently small. It's an analytical argument that you do it once and for all. The only numerical verification that you have to do is the computation. Once you obtain the homoclinic orbits, you have to do the numerical integration of the perturbation along these homoclinics. So in these papers, we have done it in a non-rigorous way, but with, let's say, great precision. There is a follow-up work with Maciej Kapiński, in which we do a computer-assisted proof. And in the computer-assisted proof, not only that we have a validated result of the existence of diffusing orbits, but we also obtain quantitative information on the diffusing orbits. And I strongly advertise here the talk by Machi, which I believe is going to be on Thursday. So thank you so much.
Questions, comments?
So the body problem is degenerate. So when you introduce the eccentricity of the planet, the new degree of freedom that you introduce is also slow. The frequency is slow. So isn't this a problem for this kind of construction?
Let me see. I'm not sure if I understand the question.
When you pass from the circular free body problem to the elliptic free body problem, you produce an additional degree of freedom. The frequency of this degree of freedom is slow. It's lower than u. The absence of the planet, so it's rather different situation from the one that one usually addresses
So the way you start this is that in the circular problem you start with a Lyapunov orbits that already have transverse intersection of the stable and unstable manifold. And so what you get when you do a small perturbation of this, so okay. No, I don't think we encounter any problem in this computation. So we can talk.
Some other question?
You have claimed that your construction is valid for any epsilon small enough.
Yes.
Okay. Do you have also lower limits on the time to see diffusive behaviors? I mean, that a lower threshold on the time that is necessary to move from a normally hyperbolic torus to another.
So in this particular work that I presented here, we did not do estimates on the diffusing time, but in the work with Kapinski, which is going to be presented, I think, Thursday, we have time estimates on the
So in
time.
principle, you can produce these estimates, and your approach is able to do that.
Yes.
Great.
And the estimates, I think they are of the order of 1 over epsilon. Which this is a priori chaotic situation, and all the 1 over epsilon is like ideal.
A very short question.
Yes.
So you have these results for epsilon small enough, you see the value of mu. No? You fix the value of mu, the value remember,
Yes.
and then you get the results for epsilon small enough.
Yes.
Is there any way to do this on tick, and because the value of mu is fixed to do the computation of the Melnikov, I imagine, no?
Yes.
Is there any trick that you can do to try to obtain results for an interval of mu's? Is it possible?
Probably through the doing like with the computer-assisted type of methods that
It would be nice to
Piotr and his group are doing. I think one can do it for a range of mu's around it. So if it works for a given value, it probably works for a small interval around these values. But on the other hand, if you want to go with mu arbitrarily close to 0, maybe one can invoke analytical arguments on the existence of transverse homoclinic intersection by Libre Martinez.
I was thinking in the talk of Lisinski of the other day that they have these methods to go to some value and then to increase the value. It could be used probably here.
Okay, I think we should proceed. So let's thank the speaker again.